In this video, we're going to look at section 3.2, which gives us a real-world example of a linear programming problem. So it combines what we're looking at in 3.1, where we find this feasible region for this set of linear inequalities. So we're going to find that feasible region where all points in that region satisfy our system of linear inequalities. And then it's going to lead us into what we're going to be looking at in section 3.3. So we won't be able to solve this yet, but it will show us exactly where we're going with section 3.3. So this is basically just one big example, and it's a furniture manufacturing problem. And it gives you exactly what is needed by this furniture manufacturer in order to create chairs and sofas. So it tells you how many hours of carpentry, finishing and upholstery it takes to create a chair and also a sofa. So we see it takes 6 hours of carpentry, an hour of finishing and 2 hours of upholstery in order to create a chair. And to create a sofa, it takes 3 hours of carpentry, an hour of finishing and 6 hours of upholstery. And then we know that from each chair that is produced and then sold, we're going to make $80 of profit. And from each sofa that is produced and sold, we're going to make $70 of profit. But we also have these constraints here that for carpentry, we have at most 96 labour hours a day that we can use towards carpentry. We have at most 18 hours a day that we can use towards finishing, and we have at most 72 hours a day to use towards upholstery. So what we want to do here is we want to try and maximize our profit subject to the fact that we have these constraints for the number of hours that we can spend for carpentry, finishing and upholstery. So in order to maximize that profit, how many chairs and how many sofas should we produce in any one day in order to maximize? Okay, that's what the question is. So let's write this problem out mathematically. If we go back to our profit, we know that we make $80 for each chair and $70 for each sofa. So if X is the number of chairs and Y is the number of sofas, then if we're trying to maximize the profit, it would be 80 times the number of chairs that you make plus 70 times the number of sofas that you make. That would be the total profit, and we're trying to maximize that. So we're trying to maximize 80 times X plus 70 times Y. Then we have these constraints that we are subject to, which is the number of hours of labour. So here we know that we can have 6 hours of carpentry for a chair and 3 hours of carpentry for a sofa. So 6 times the number of chairs plus 3 times the number of sofas has to be at most 96 hours. Okay, you can't have more than 96 hours in total spent on making these chairs and sofas in terms of carpentry. So that tells me that 6x plus 3y has to be less than or equal to 96. I can't go over 96 hours. Same goes for finishing and upholstery. So 1 times x plus 1 times y can be at most 18 for finishing. So I have x plus y is less than or equal to 18. And then I have 2 hours of upholstery for a chair, so 2 times x plus 6 times y for a sofa is at most 72 hours. So that gives me 2x plus 6y is less than or equal to 72. Okay, so each one of these constraints tells me how many hours of carpentry, finishing and upholstery I can have dependent on the number of chairs and sofas that I'm creating. Obviously, the number of chairs and sofas has to each be greater than or equal to 0. I can't have a negative number of chairs and sofas that I'm making. So we also have the additional constraints that x and y have to both be greater than or equal to 0. So this gives me my full problem. I'm trying to maximize the profit subject to these constraints of labour hours. When you do this problem, we're going to forget the top part for now, and we're going to just look at these constraints. The maximization problem is what's going to come in 3.3, but we can at least find the feasible region of these constraints. So where are we going to find that maximum? What region are we going to find that maximum in? We can't yet find the maximum profit, but we can at least find that region where we're going to find the X and Y that's going to maximize our profit. Okay. So what I'm going to do here is exactly what we have done in 3.1. I'm going to rearrange each of my constraints so that they are in slope-intercept form. Then you can go ahead and graph each one of those as though they were an equality. So you're going to go and find the intercepts for each line. Then once you've done that, you're going to see if the origin is on the correct side of the line or not. So you're going to see if the origin satisfies the inequality. If it does, then we know that the origin is on the correct side of the line. And if not, you know it's on the wrong side. And so then you can get rid of whichever side of the line does not satisfy the constraint. So let's go ahead and rearrange these. If you rearrange this first one, you should get that y is less than or equal to negative 2x plus 32. So that is now in slope-intercept form. The next one is y is less than or equal to negative x plus 18. And the last one is y is less than or equal to negative 1/3 x plus 12. And then the last two can remain the same. So I know that I am looking in that top right-hand quadrant. That's where my solution is going to be, just because we know that both x and y have to be greater than or equal to 0. So I know I'm looking in that top right-hand quadrant of my xy plane. Then I've got those constraints, so I'm going to graph each of those as though they were a line, so as though each one were an equality, and then we can treat them as inequalities again and look at whether the origin is on the correct side or not on the correct side. So does the origin actually satisfy each of these inequalities? It turns out the origin satisfies all three. So if you then look at the graph, you have each of the lines have been graphed. The origin, if we go back to our constraints here, the origin satisfies all three of these constraints. So I know that the origin is on the correct side of the line. So for each one of my three lines, I can get rid of everything above those lines. I also know that x and y have to be greater than or equal to 0. So I can get rid of everything where x is negative and everything where y is negative. So it turns out that my feasible region, it includes the lines because remember they are all less than or equal to, so we have to also consider the lines, but it's everywhere on that yellow line, so within the yellow line and on the yellow line. Okay, that is my feasible region. What we're going to do in 3.3 is not only find the feasible region, but we're going to try and maximize a particular function subject to those constraints. So we're going to find where the maximum of 80x plus 70y is by using an x and y within that region. And where can we find that particular x and y that will give us that maximum? Okay, so that's what we're going to look at in 3.3, but this is a really good real-world example of finding that feasible region, and then we're going to incorporate our section 3.3 of actually maximizing, or in some cases you're going to be minimizing a particular function within that feasible region. So that's where we're going to go next time in section 3.3.